Welcome back. Today, we're diving into the fundamentals of network architecture for private cloud AI. Getting this right is absolutely crucial. It's basically the backbone of any AI initiative that's going to succeed. Okay, before we jump in, just a quick but really important heads up. As you can see, this is Module 4 of a 15-part tutorial. Now, everything we're talking about today is an overview based on a super comprehensive report by Virtualization Options LLC. That means it's for general guidance, it comes without a warranty, and it is definitely not legal or financial advice. We always recommend that you chat with your own financial, technical, and legal pros before you take any action. And just remember, these modules, they really only scratch the surface of what's in the full research report. So to really wrap our heads around AI networking, let's use an analogy. I want you to picture your entire infrastructure as this big, bustling city. For this city to actually work, to thrive really, it depends on two completely different kinds of superhighways. Each one is totally unique and absolutely vital. So let's break down these two critical data flows. In the networking world, we call them north-south and east-west traffic. And trust me, understanding the difference here is the first, most important step to designing a network that won't end up bottlenecking all your expensive AI hardware. All right, first up, north-south traffic. Just think of this as the main artery connecting your AI city to everything else. It's how you bring in those massive training data sets from the cloud. It's how your users send requests to your models, and it's how you shoot the results back out. It's all about talking to the outside world. And then you've got east-west traffic. Now, this is the internal communication. This is the lifeblood of the whole operation. It's that constant, super high-speed chatter happening between hundreds of servers and GPUs while they're all working together on these really complex training jobs. This is where the real intense, demanding work happens. Let's take a closer look at that north-south connection, shall we? This is the artery that connects your whole AI cluster to the outside world. And believe me, its unique demands can make or break your user-facing apps. North-south traffic is a real tricky balancing act. On one hand, you need massive bandwidth. We're talking 10 to 40 gigabits per second, just to pull in those huge training data sets. But at the same time, you need it to be rock solid and reliable, which usually means having two different internet providers for automatic failover. And so critically, you need low latency. For anything happening in real time, every millisecond counts. The goal is usually under 100 milliseconds for a user to make a request and get a response. In this slide, it just lays out that layered defense-in-depth approach perfectly. You start at the very edge with your redundant internet connections and DDoS protection. Then you might have dedicated circuits, something like an AWS Direct Connect, to just bypass the public internet entirely for better security and speed. As you get closer to your core, you've got API gateways managing all the requests, and then, finally, these huge high-capacity routers that make sure all this traffic gets exactly where it needs to go. Okay, let's switch gears and move to the internal superhighway. Because this is where AI puts the most extreme, the most technically demanding requirements on your network. This is the very fabric that holds your entire GPU cluster together. And really, don't underestimate this point. The performance of your multi-million-dollar GPU cluster is directly, and I mean directly, tied to the quality of this east-west fabric. If your network here is inadequate, your GPUs are just going to spend more time waiting around for data than actually computing. And that is a complete waste of your investment. So here's the crucial thing to understand. During distributed training, you've got hundreds of GPUs that need to sync up their work after every single step. This creates something called collective operations, which is basically a fancy way of saying every server tries to talk to every other server at the exact same time. These synchronized bursts can create massive network traffic jams that will absolutely cripple performance if the network isn't built for it. This incredible challenge has basically created a high-stakes technology battle. There are two dominant approaches for building this internal superhighway, and the choice you make between them has huge implications for performance, cost, and just how complex it is to run. This table just lays out the trade-offs perfectly. On one side, you've got InfiniBand. This is the gold standard, what the world's biggest AI supercomputers use. It offers mind-bogglingly low, sub-microsecond latency. On the other side, you've got RoC. That stands for RDMA over Converged Ethernet. It's a really clever way to get InfiniBand-like performance, but on the familiar Ethernet networks that most data centers already have. The magic word here is RDMA, which lets servers bypass their main CPUs and talk directly to each other's memory, which just slashes latency. Now, RoC's latency is a little higher than InfiniBand's, but its big appeal is that you can use existing tools and expertise. but I'll warn you, it requires meticulous, expert-level configuration to get it right. So whether you choose InfiniBand or ROS, the question is, how do you make sure you are squeezing every single ounce of performance out of that investment? Well, it all comes down to careful tuning and optimization. So, here are a few essential techniques that can make a massive difference. Simple tweaks like enabling jumbo frames, which just means sending data in larger packets to reduce overhead. That can have a huge impact. It's also vital to isolate your different kinds of traffic. You can't have a storage backup job suddenly getting in the way of a time-sensitive training run. And finally, you have to monitor everything with sub-second precision to catch and fix those tiny microbursts of traffic that can silently just kill your performance. So, as you're planning out your AI infrastructure, I want you to remember this. The network, it isn't just plumbing. It's the high-performance fabric that weaves your compute, your storage, and your data all together. And the crucial question you have to ask yourself is that fabric strong enough? Not just for today's models, but for the even more demanding AI of tomorrow?